time in my academic career to give a talk in my homeland. So thank you for that. So, all right, before I start, I would like to just give you an overview of where I'm located. Not so many people know where Aarhus University is. It's in Denmark and Jutland, this little spot here, the second largest city in Denmark. And this is the view of the city, the campus of the university somewhere around here, and engineering department. It's a building by the harbor. So I just want to let you know also that if you know anyone interested in applying for positions, we currently have openings for assistant and associate professors on this particular areas of interest here. So some acknowledgements. This work has been done with Daniel Renaud Kirchhoff for an Aalto University, Douglas Holmes Group at Boston University, and also Harold Park and David Campbell at Boston University. They're mostly responsible for the MED simulations that you'll see during this talk. Okay, so what is this talk all about? It's about Kirigami, and this is something that's probably familiar to everyone in this room. So if you have ever been cheesy enough to give a card like this, you've collaborated with this origami idea, but it's basically cutting paper and pulling on it in order to form shapes in three-dimensional space, right? So it's a very straightforward idea, and here it's just a simple example. I have a thin sheet, like a membrane, and then I pull on it, and you can see all the cuts. And this is somewhat unintuitive because you basically take a material that doesn't stretch very much, and by making those changes, those topological changes, as it has been noted, we are able to achieve large structural strengths. So this has been done already by a variety of groups. So the first one that I must note here is the group by Randy. There are some people in this room who contributed as well, like Daniel, and so this work is basically to the best of my knowledge, the first one in the physics community to attack this problem. So that serves as inspiration to continue on to try to understand how to sort of use these types of geometries to regulate topography and geometry of surfaces. So there are other groups interested in this. So in the sense of generating shapes, the group of José Bica and Benoit Roman at the SPCI. And also there has been recently a lot of effort to try to utilize these sheets in order to generate some interesting mechanical properties, as you can see in the work by Katia Bertoldi here, and also from some people in the audience, Michael Moshe and Shankar is also here. We'll be talking about this tomorrow. So, all right. So, as far as the interest in the community, the engineering community to apply these structures, there are some obvious applications, which is microfabrication of surfaces. People have been doing this etching of silicon wafers, and they are able to carve out some of these Kirigami structures, and for whatever interest they might have, like I showed you here, for large strains of these structures that are usually stiff. So, or to avoid types of localization like this, where you have cuts that are made, and then you can reduce some types of unwanted forms of localization on your thin sheet. A lot of flexible electronics community most recently here in the group of John Rogers, that I think it's quite a natural way of think of these structures, that you can carve out these cuts and be able to sort of allow that this could sort of wrap around surfaces, curved surfaces, or be more compliant to the skin, and in the case of the example shown here, in a more natural way. So this is not working. Yeah, it's working. All right. So I think the specific application that I would like you to keep in mind as I go through my talk is the idea of actuators. So there are some examples of some of these micro optical systems where you have either lenses or microscopes that you want to be able to move the parts of your system in an intelligent manner, and most recently this is being used. This sort of springs here, which are memory-shaped alloys, and you pass electric current through them, and then you can move them around. But the disadvantage in this case is that it needs lots of actuators in order to attain a complicated motion in space. So the question that was left to us is, can you design a structure with simple linear actuation and control the motion of structures in space in more complicated manners, right? So, and then there is obviously the question of making those energy efficient, and if you are dealing with structures that are like this paper or Mylar, at the scale that you can handle, hold with your hands, can you scale this down to structures that are made of materials at that scale? So this is a question that one could ask. Or even lower in dimensions in the case of graphene sheets, which I will talk about in a bit. So, okay. So I just go straight to the point. So this is the main sort of result of our paper, and I will try to pedal back and explain a few features of all of this. But I think this the goal of our paper was to be able to design at least 4 forms of actuation, namely roll, pitch, yaw, and lift. And of course, a lot of this was there in the lab with trial and error, but then later by backwards design, we try to understand some of the species and bits and look at simpler structures, because those are rather complicated because they involve many cuts in them. But basically, you can see that you have a thin sheet of Mylar, which is this kind of material here, like some sort of plastic, right? And then we make the cuts, and we are pulling along the x direction. And here at this little coordinate system, I'm indicating the type of motion that you see. In this case, rotation about the x-axis, right? And then we have pitch, which is, excuse me. Those things tend to do this, right? And then we have pitch, which is rotation about the y-axis, yaw, and lift. So what you pull along the x-axis, all of them, yeah, okay. So what you see in those images here are the experimental setup we had, and here are finite element simulations that I've performed using shell element and nonlinear elasticity for account for the large deflections of the systems. Yeah. Yes. Yes. Okay. Yeah. So I'll get to that in the next slide. We've been able to combine, but then in order to explain the mechanism is something that hopefully later I will shed some light into it. Okay. Yeah. So So, okay, so the first one question is to combine the modes, but before that, we thought about the simple question of scaling and homogenization. So you can think about that each one of those modes that I showed previously can serve as a unit cell of an entire system, right? But also, like you already asked, you can think about combining those modes, so like in this case over here, right? Where you have first pitch and lift at the very end, right? Or something more complicated like this one, which is a mixture of several different modes. So, okay, so what we decide to do next, just to show something slightly more quantitative about this, is to perform, along with the finite element simulation, some molecular dynamics, and we are using this type of model here. So the sheet is made of this unit cell, which is the MOS2, right? And the choice of potential is the Stiller-Weber potential, and the reason for that is because it yields a well-defined bending rigidity that can be extracted from this potential here, as you can see here in the fit of the energy density and the bending curvature by doing simple bending test on a flat sheet of this material. And then we reproduce one of our modes, which is this this guy over here. So this is the simulations, and then the next slide I show you something slightly more quantitative, which is the measurement of the deformation of these modes. So the way to read this plot here is the deformation along the x-axis, the extension of the entire sheet. On this side of the y-axis is just measuring the out-of-plane deflection of the lift mode, and here we put the measure of the rotation of all the other modes, and then they are color-coded here respectively. So the solid lines here and the dashed lines are the finite element method simulation, and here for the case of the molecular dynamics, we see that there is some effect of thermal fluctuation there. It's not perfectly sitting on top of the results that we got for the macro scale. However, they seem to be qualitatively reproducing the same sort of mechanism that we see in the macro scale. Okay. So, all right. So now I just take a step back, and then I will try to give you some insight of the way I see this problem now, and what are the types of fundamental questions that might be related to this, and then I'll try to connect back with the mechanisms of the structures that I just shown you. So Benny gave a talk yesterday, and he yesterday or the day before yesterday, I don't remember, but he spoke about this balance, and several other people have been using this idea as well, so I won't spend so much time, but just remind you that we are dealing with thin sheets that that undergo in-plane stretching, right, like this, and out-of-plane bending, and those two contributions are important to understand the energetic balance of these structures. The way that I'm trying to sell this problem is to understand what are the types of deformation motifs that lead to this Kirigami deformation. So, and I will do an analogy with a very well-known problem that has been described back in the 90s, which is the problem of the Econ and the stretching ridge, right? So this is a problem where you have these types of corner singularities here that they live on the bulk of the sheet. And if you make two of them, there is a tension line connecting those two singularities that is called the stretching ridge, and that's how the sheet chooses to penalize stretching energy, and everywhere else the sheet is bending, right, isometrically, right? Let's say 10 minutes already. Wow. Okay. So and then here, what we have is that those types of localizations, they happen at the boundary of the system. So we've made several cuts, and this is now being this localization that happens around the crack tip, and we want to understand how those localizations are interacting within the sheet. The interesting aspect of this is that this new type of localization at the boundary, it's fairly unstable, right? So if you see a system of this kind, and here is the force displacement, you'll see a formation of a state over here, and the state is not stable, and it snaps into a different state, and then when you go back in the formation collected, this hysteresis loop over there. Okay. So what's the deal with this then? So what's happening over here is something that is sort of dual to the decon problem, right? So you have a decon problem, and as I mentioned, you have a line of tension between the 2 points. And what's happening here, it's exactly the opposite. You have an axis angle over there, and in between there is a line of compression. And those two states are what you will see here. And I have a somewhat an heuristic argument for why those are the two states, whereas this is somewhat stable. So those singularities can move, and I think Effie has worked on motion of singularities through a sheet, but they are way more stable than these ones. Those are they change conformation quite easily. Okay. All right, so the way that I'm going to look into this is by sort of taking, yes, sure. Yeah, so I will try to not necessarily. I will try to lay out the argument. I think the question is still open, but let's see if that answers your question. Okay. It's related to the amount of bending energy that each one of those states will be able to realize. So so here we have this decon and econ dichotomy here that I'm trying to put forward, and the way I'm going to look at this to make my life easier is to discretize the system. So it has been shown that this discretized version describes quite well the systems. So in order to be able to say something quantitative about this, I'm going to be using the Gauss map, which is basically taking the normals of a surface, the surface here, taking the normals of a surface and mapping onto the unit sphere, and then you can show that the Gaussian curvature is proportional to the solid angle, or the angle of this area traced by the path of this normals here. So, and then when you have folds, basically you have the normal pointing all in one direction at one side, and the other side is pointing in another direction. And as you go across the fold, it traces an arc on the unit sphere. So I'm going to be using this argument all the time here. So the case of the decon and decon interaction, I just put it here. This is what we have, right? So the decon, you go around the loop, and then you map all these normals onto the unit sphere. And here I'm looking at small deflections just for simplicity of the talk here, where you see around the pole of the unit sphere a figure like this, and the normals are at the corners of this figure, and the angles of the folds are the arcs that are traced by these normals as they go from one side to the other. And as you calculate the area of this object, because the orientation here is opposite to the orientation there, then you conclude that the Gaussian curvature is equals to 0, right? And you can do the same thing here for the decon interaction and conclude the same thing throughout the sheet. So on the other hand, the case of the econ, right? So you capture an area there, and that area has been shown by Gauss that is proportional to the amount of wedge that you have to impose to deform this structure. And but at the same time, you can think of that there is another type of configuration here that can hold the same area but it has, let's say, less bending energy, because in this discretized case, all the bending energy is concentrated at the folds. So the argument here is that when you put those two together, you have two different states where one has less bending energy than the other. So if you happen to fall into this state by some initial imperfection in the system, you can potentially frustrate this to fall into this system here, which has less bending energy than the first. So 5 minutes, okay. So then we started to look back into another simple case, which is this at the middle. We did a bunch of experiments here to track the deformation of the system. And so I'll rush through this argument here because I want to show something else, but I just point out that we have a scaling argument here for the amount of deflection of the out-of-plane deformation of the structure, and in comparison with finite element method and molecular dynamics and the experiments, they seem to all collapse onto this scaling law here that we have derived. So, but then I go back to the Gauss map story where you can look at the discretized structure, right? So, the same story that I showed before. This has been sort of indicated by Keith Seffen in this nice paper over here. So the idea of this is that you have an axis angle here and there, and then you would think that there are only two econs. But then as you go around and as you deform the structure, much like these guys over here, right? So this is the discretized structure. And what you see is that all these panels remain flat and they rotate. And they all contribute with an angle gamma. Right, so you cannot match up all the Gaussian curvature that this system has by only accounting for these two econs there. But there is actually two other econs that go towards the boundary of the system in the opposite direction. And when you account for all these different guys there, if you make the Gauss map, you can compute the total Gaussian curvature of this. So we use this system in order to do some high school geometry here, because this is all on the plane. And then we can relate the out-of-plane deflections of the structure by just measuring distances on a unit sphere over there. So it turns out nicely that that we get the same scaling that we've derived from the continuum model, which is given by the square root of the amount of deformation over the width of the sheet. Okay. One thing regarding the entire mechanism of the other modes that I showed at the beginning, the more complicated modes that we've noticed, and here I don't have time to go into details, but I'm happy to talk afterwards, is that when you look at these structures, remember this was the roll mode, they had that complicated deformation in space, is that if you look at the network of cracks within the structure here, you can think of changing the length of this crack so that this network becomes either concave or convex. Concave here or convex here. And it turns out that the balance between bending stretching energy switches more or less about this measure of convexity, because it switches from convex to concave right about 1 here. And we've noticed that all these mechanisms, they share the very same story, is that the idea of convexity of the network of cracks is telling you, indicating when you get rotations of the system and when you don't, right? Because if this just this crack was about smaller than this, you would be trapped onto a configuration that looks like this. The system would be completely stressed. So there is some sort of order parameter here that tells you that there is a phase transition regarding the type of conformation you can get into these systems. So I think I'm out of time, but I will leave up my conclusions, and I thank you for listening.